From now till the end of chapter 9, we are focusing on heterolytic bond cleavage. You are going to learn about homolytic bond cleavage in organic chemistry too, but in this course we are just focusing on heterolytic bond cleavage. But before we talk about those type of reactions, first we need to think about and recognize what we call nucleophile and electrophile. So these two compounds are basically reacting with each other, and electrons flow from one to another one. So the nucleophile, which comes from Greek meaning nucleus lover, is an electron-rich center that has the ability to react with a positive or partially positive atom. So it is carrying the meaning on its name. It is a nucleus lover. It loves the positive charge. If you remember from acid and base chapter, something that's electron rich is a Lewis base. So basically Lewis bases are examples of the nucleophile. So any atoms that has regions with a high electron density on it, it can act as nucleophile. For example, ethoxide, it has lone pair of electrons on oxygen, so that oxygen can act as nucleophile. Ethanol also has lone pairs of electrons on oxygen, so it can also act as nucleophile. It doesn't have to have negative charge, it has lone pair of electrons on it. Even the electrons in the pi bond, it is a source of electrons, so it can act as nucleophile. Now, how about electrophile? So electrophile means electron lover. So it is an electron deficient atom that can accept pair of electrons. So we can think of Lewis acids for electrophiles. For example, carbocation, it has positively charged carbon and an MTP orbital, which can accept pair of electrons. Another example is an alkyl halide. Specifically here we have alkyl chloride. So we know that chlorine is more electronegative than carbon. It pulls the bonding electron toward it. Therefore, chlorine becomes partially negative and carbon becomes partially positive. So this carbon is our electrophile. Just pay attention that chlorine cannot act as nucleophile because if it attacks another atom, it would get positive formal charge, which makes the whole species very reactive species. So chlorine cannot be nucleophile. This structure only for the most part act as electrophile. So in general we can say in reactions, nucleophiles that are electron rich, that are our source of electrons, can attack the electrophiles because they have empty orbitals and they can accept the lone pair of electrons. Mechanisms again. So we show how a reaction takes place using curved arrows, and we show the flow of electrons using those arrows. We used such a thing before in acid and base reactions. We are going to complete our knowledge about arrow pushing process in this part. There are 4 characteristic patterns that we can recognize while drawing mechanisms. The first pattern is nucleophilic attack, and in this pattern, nucleophile attacks an electrophile. So sometimes we show nucleophile as Nu and showing a lone pair, and electrophile shown as E with the plus charge. So if we have these two starting materials, these two, bromine is our nucleophile because it possesses the lone pair of electrons, and we have carbocation which has MTP orbital. Therefore, the tail of the arrow is placed on the lone pair of electrons, and the head goes to electrophile to show the flow of electrons from the nucleophile to electrophile and forming this product. So this is the new bond between the carbocation and our nucleophile. Sometimes we need to use 2 curved arrows to show the nucleophilic attack. So if you look at this example here, methanol and acid chloride. Okay, so the first step is to identify the nucleophile and electrophile. We already talked about it. Methanol is an alcohol. An alcohol has lone pair of electrons on oxygen, so it can act as nucleophile. And this structure right here is our electrophile. How do I know that? Because if you remember, this structure can do resonance. And when you draw the resonance structure for that, you notice that this carbon gets the partial positive charge. So the carbon of carbonyl is carbon oxygen double bond, so the carbon of carbonyl is our electrophile. Okay, now to show the arrow pushing, nucleophile attacks the electrophile with its lone pair of electrons. Then we need to push this pi bond up to oxygen, because if we don't do that, this carbon would get more than 8 electrons around it, which is completely incorrect. Therefore, we need to push this lone pair of electrons on oxygen to give enough space to the nucleophile to bond to that structure. Now we need to draw the product. So I first draw my acid chloride. So I open this double bond and pushes the electron on oxygen. So oxygen gets the negative charge. We have monovalent oxygen. It is negatively charged. Now this is the bond, the new bond between the oxygen in alcohol, and to that oxygen we have hydrogen attached and we have methyl group attached. So don't forget, you need to calculate the formal charge as well. Oxygen with 3 bonds is positively charged. The second pattern is loss of leaving group. Leaving group is abbreviated as Lg in organic chemistry. Now, what is the definition of leaving group? So, leaving group is an atom or a group of atoms that departs with a pair of electrons from the structure it was attached to. We can have some common leaving groups such as water, ammonia, halogens such as chlorine, bromine, iodine. Now, what's happening in this process? So if you look at this example and compare the starting material with the products, in the starting material, bromine has 3 lone pair of electrons. However, in the product, it has 4 lone pair of electrons. This carbon is neutral in the starting material. However, it is positively charged in the product. So what's happening here? Bromine took the bonding electron, left the molecule, and we show this process with one curved arrow to form the bromide anion and the carbocation. Let's look at the example here. Okay, so if we compare the starting material with the products, it is obvious that chlorine has left the molecule. So we can start by drawing an arrow to show loss of leaving group. Okay, and after the leaving group leaves the molecule, this carbon becomes positively charged. Okay, now if you compare these two structures, how can I get this structure starting from this one? So what I can recognize in this is that pi conjugated system. So this structure can contribute in resonance. So let me number all the carbons. Okay. Okay, so this is carbon 1, 2, 3. So while drawing the resonance structure, now the double bond is between carbon 2 and 3, between carbon 4 and 5, 6 and 7. Carbon 8 lost the electrons, so it becomes positively charged. These two structures are completely identical. So this is the resonance structure for this pi conjugated system after loss of leaving group. This resonance structure is more stable than this one. We have a tertiary carbocation here. However, here we have a secondary carbocation. Tertiary carbocation is more stable than secondary carbocation. We call that tertiary because it has 3 alkyl groups attached to it. We call this one secondary because it has 2 alkyl groups attached to it. So don't worry about these terminologies. We are going to talk about them in the next slides. The third pattern is proton transfer. We already talked about it in chapter 3 if you remember from acid and base reactions. The base attacks the acid to take the proton and forms the product. So this is what's happening here. This oxygen on a carbonyl, it has 2 lone pair of electrons, so it can act as a source of electrons for us. Then it can attack the acid to take the proton, and then the bonding electron moves to the next atom, which is oxygen, to form this product and water. So as we talked before, to show the proton transfer, we are using 2 curved arrows. However, there are some situations where we need to use multiple arrows. So look at this example. Okay. Hydroxide is our base. It can attack the most acidic proton in the molecule, which is this hydrogen right here. So it can attack that and pushes the bonding electrons towards the carbon to form this product plus water. Now this product can do resonance. We have allylic lone pair. Use 2 arrows to show the resonance. Calculate the formal charge. Oxygen gets the negative charge. So between these two structures, which one is more stable? Obviously the bottom one, because the negative charge is on oxygen. However, in the top, the negative charge is on carbon. Therefore, sometimes we can combine this resonance with the proton transfer arrows, and we can show everything together. So this arrow attacks the hydrogen, the base attacks the most acidic proton. This bonding electron moves here and pushes this lone pair to get this structure. The last pattern is rearrangements. which is very important, especially when we are forming carbocations and radicals in the mechanism. So there are several kinds of rearrangements, but for now we are focusing exclusively on carbocation rearrangements. Something that we are talking about here is true for radicals as well. However, you are going to learn about radicals in organic chemistry too. For organic 1, we are just focusing on carbocations. So carbocations can be stabilized by neighboring alkyl group by a process called hyperconjugation. So what does that mean? Let me redraw this carbocation. This carbocation has an alkyl group attached to it. So we know that the hybridization on carbocation is sp2, and carbocation also has an empty p orbital on a positively charged carbon. So this p orbital can be stabilized by a process which we call hyperconjugation, meaning that the neighboring CH bonds right here, they will place some of their electron density into the p orbital. And this process makes the p orbital stable. So hyperconjugation is the stabilizing factor for empty p orbital. And the more alkyl groups attached to this positively charged carbon, the more sharing electrons can happen and the carbocation would be more stable. So as I just mentioned, the more alkyl groups connected to the carbocation, the more stable the carbocation would be. So this R group means we have an alkyl group attached to the carbocation. So when the carbocation has 3 hydrogens attached to it, we call that methyl carbocation, and it is the least stable carbocation. When we have 1 alkyl group attached to the carbocation, we call that primary carbocation. And an example for that can be this alkyl group, CH3. So there is 1 alkyl group attached to the carbocation. We call that primary carbocation. And primary carbocation is more stable than methyl. It is obvious because we have more CH bonds that can participate in hyperconjugation. And we can have secondary carbocation when we have 2 alkyl groups attached to the carbocation. So an example can be like this. So the alkyl group shouldn't be only methyl, it can be ethyl, propyl, basically any kind of alkyl groups attached to the carbocation helps with stabilizing the carbocation. And the secondary carbocation is more stable than primary because obviously we have even more CH bonds helping with hyperconjugation. And the last one is tertiary carbocation, where we have 3 alkyl groups attached to the carbocation. And this can be an example. So the tertiary carbocation is the most stable carbocation. Now that we know different types of carbocations, let's see how carbocation can undergo rearrangement. There are 2 ways that an unstable carbocation can rearrange to form the more stable one during the reaction. The first one is 1,2 hydride shift, or simply we can say hydride shift. So previously we talked about proton. We know that proton is the hydrogen atom without a lone pair of electrons. However, hydride is the hydrogen atom with a lone pair of electrons. It is negatively charged hydrogen. And to show that hydride shift is happening, we can simply write it on top of the arrow. So now let's compare these 2 structures. The first structure we have a carbocation. It has two alkyl groups attached to it. We call that secondary carbocation, and we show it this way. The next structure, we have a carbocation again, but the carbocation has three alkyl groups attached to it. This is the tertiary carbocation. We know that tertiary carbocation is more stable than secondary. Therefore, the secondary carbocation undergoes the hydride shift to form the more stable carbocation. Now, how does this happen? So what we are doing here is hydrogen will take the bonding electrons and move them to the positively charged carbon. Now this carbon has a full octet, so it doesn't have the positive charge anymore. However, this carbon lost electrons, therefore it becomes positive. So this process is happening to form the more stable carbocation. The next rearrangement is 1,2-methide shift, or what we call methyl shift. So here, instead of hydride, methyl group migrates to the positively charged carbon. Negatively charged methyl group is migrating here, and we can write methyl shift on top of the arrow. So again, let's look at these two structures. This one has two alkyl groups attached to it, this carbocation. So again, it is secondary. And this carbocation has three carbons attached to it. So three alkyl groups, it's tertiary. Now, the neighboring carbon doesn't have any hydrogen to shift. However, the methyl group can take the electrons and move to the positively charged carbon to make a full octet here and gives the positive charge to this carbon to form the more stable carbocation. So a few important points. First, carbocation rearrangement generally don't occur on tertiary position unless it produces resonance stabilized product. So let's look at this structure. Okay, and we have positive charge here. So let me draw the hydrogen connected here. So this carbocation is tertiary. So we expect that doesn't do any hydride shift or methyl shift. However, this carbocation can undergo hydride shift. So the hydride moves here. Okay, so this is the hydride that moved here and makes this carbon positively charged. Now, if you look at this structure, this positive charge is allylic to double bond, so it can have resonance. Okay, so this carbocation is both tertiary and resonance stabilized. So hydride shift can happen here. The next point is that sometimes carbocation rearrangements occur via migration of alkyl group, something other than methyl. So let's look at this example. We have this carbocation which undergoes alkyl shift to form the more stable carbocation. So the first structure, this is a carbocation. We have primary carbocation. It is connected to one alkyl group. It is primary, and we have a 5-member ring here. Now the second one, we have secondary carbocation, and we have a 6-member ring. So which means that by doing the alkyl shift, not only we are making the more stable carbocation, but also we are reducing the ring strength, which is favored. So how does this happen? Let's number all the carbons here, and also in the product. So what's happening here? We are breaking the bond between carbon 2 and carbon 6. Okay. And we are shifting the electron density from carbon 2 to carbon 1. So the electron density is moving from 2 to 1. Therefore, in the product, we have a bond between carbon 1 and carbon 6. Now that we moved the electron density from carbon 2 lacks electrons, therefore it becomes positively charged. And then we have the rest of the carbons connected to one another. So by doing this, as I mentioned, we have more stable carbocation and less ring strength, which is always favored. Let's combine the patterns that we learned and define each step of this mechanism using those patterns. So by the end of chapter 6, I really don't expect you to draw such a mechanism. You will by the end of this course. But for now, you should be able to identify each step and recognize those patterns. So let's look at the first step of that mechanism. Compare the starting materials with the products. HBr lost the proton and converted to bromide. And we have an alcohol here that gained the proton and converted to this molecule. So this is an acid and base reaction. It's a proton transfer step. So the oxygen attacks the proton and move the bonding electrons over bromine. So then let's look at the next step. Compare the starting material with the products. So if I compare this molecule with this structure, it is obvious that I lost the water molecule here. So it is loss of leaving group. And to show that leaving group is leaving, we write negative H2O on top of the arrow. So meaning that we are losing water. So the leaving group takes the bonding electrons and leaves the molecule. Therefore, this carbon would get the positive charge. So how about the third step? If we compare the starting material and the product, we have carbocation. So whenever you have carbocation, think about rearrangement. If that carbocation can do rearrangement to form the more stable carbocation, it will definitely do it. So here I have secondary carbocation, which converted to tertiary carbocation. So obviously rearrangement has happened here. Now, what type of rearrangement do we have here? Is that hydride shift or methyl shift? So if you compare these two structures, The positive charge is transferred to the third carbon. The third carbon in the first structure has 2 methyl attached to it. However, in the product, it has 1 methyl attached to it. So it is obvious that methyl group has moved here. So this is a methyl shift. Now, how about the last step? So compare the starting material with the products. I have carbocation, which can act as electrophile for me. And I have bromide, which is a nucleophile. So it is a nucleophilic attack. The nucleophile attacks the electrophile to form the products. If we look at the products, they are 2 different structures. And the first one, bromine is coming out of the plane of the page, and in the second one, bromine is going into the plane of the page. So we know what are they to one another. They are enantiomers. So we made a mixture of enantiomers. Now, why we made a mixture of enantiomers here? So if you look at the carbocation, we know that the hybridization on carbocation is sp2. An sp2 hybridization without a lone pair of electrons gives the geometry of trigonal planar. So since the carbocation has the planar geometry, that means the nucleophile has the chance to attack the carbocation from the top or from the bottom. If it attacks it from the top, the bromine is coming out of the plane of the page. And if attacks the carbocation from the bottom, bromine is going into the plane of the page. The chance of attacking the carbocation from the top and from the bottom is equal, meaning that we are making 50-50% mixture of both enantiomers. And the equal mixture of enantiomers is called racemic mixture. We are going to talk about that later in chapter 7. So we made a racemic mixture of enantiomers. In most of the reactions, we are making equal mixture of enantiomers. So basically, we are making racemic mixture, unless steric plays a role, which we are going to talk about later. Now let's look at another example here. Okay, so sodium is the counter ion and we have SH. This is an example of a substitution reaction, which we are going to talk about in chapter 7. So the 2 things you need to look for here is nucleophile and electrophile. If you can find those 2, you can easily show nucleophile attacks the electrophile with curved arrow pushing. So if I look at sulfur, sulfur is the nucleophile here because it has lone pair of electrons on it. So this is the nucleophile. And if I look at this structure, I know bromine is more electronegative than carbon, so it pulls the bonding electron toward it, makes the carbon to have partial positive charge. So this structure contains the electrophilic carbon. Now that I know my electrophile and nucleophile, I can simply show that nucleophile attacks the electrophile. Okay, so now when sulfur is attacking, the carbon would get more than octet unless one of the connected group to it leaves. So this carbon has bromine attached to it and also a hydrogen attached to it. So which one would leave? If hydrogen leaves, hydrogen will bear a negative charge on it. If bromine leaves, bromine would bear a negative charge on it. So which one can stabilize the negative charge better? Obviously bromine, because bromine is more electronegative. Therefore, after attacking the nucleophile, this bond breaks and the electrons move over the bromine. So we are gonna have this structure. So basically we are combining the nucleophilic attack and loss of leaving group at the same time. And sodium, bromine. So I would like to mention that sodium is a counter ion here, so we can basically ignore it while drawing the mechanism. It is just there to stabilize the negative charge, so we can just ignore it. It doesn't play any role here.